Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss oxidation states of transition elements. Last class I have discussed physical properties. Just I started, now I will continue with oxidation states. One of the notable features of a transition element is the great variety of oxidation state it may show in the compounds. Scandium, titanium, vanadium, chromium, manganese, ferrous, cobalt, nickel, copper, jadon. In these compounds, except scandium, Sc has only one oxidation state, +3. Titanium has 3 oxidation state, +2, +3, +4. And vanadium has 5 oxidation state, +2, +3, +4, +5. Chromium has 6 oxidation state, +2, +3, +4, +5, +6. And manganese Mn has maximum 7 oxidation state, +2, +3, +4, +5, +6, +7. Remember it. Manganese has maximum oxidation state, +2, +3, +4, +5, +6, +7. Ferrous has 4 oxidation state, +2, +3, +4 and +6, no +5, +2, +3, +4 and +6. Cobalt has 3 oxidation state, +2, +3, +4. Nickel also have same number, 3 oxidation states, +2, +3, +4. Copper has only 2 oxidation state, +1 and +2. And jadon has only 1 oxidation state, +2. That I have briefed you about oxidation state of first row transition metals. The most common ones are what I have discussed. In that also this titanium, scandium I told you +3, only one +3, but in titanium +4 is common, and in vanadium +5 is common, and in chromium +3 and +6 is common, and in manganese +2 and +7 is common, and in ferrous +2, +3 is common, and in cobalt +2, +3 is common, and in nickel +2 is common, and in copper +2 is common, and jadon only one is there, +2. The elements which give the greatest number of oxidation states occur in or near the middle of the series. Manganese, for example, exhibits all the oxidation state from +2 to +7. The lesser number of oxidation states at the extreme ends stems from either too few electrons to lose or share, means scandium and titanium, or too many d orbitals, Actually, generally D block, as you will go scandium onward, D block electrons, number of electrons will increase. Okay. Again, I am telling you, the lesser number of oxidation states at the ends stem from either too few electrons to lose or share, as for example scandium and titanium, or too many d electrons, hence fewer orbitals available in which to share electron with others for higher valence. Thus, early in the series, scandium is virtually unknown. Early in the series, that is scandium second, is virtually unknown, and titanium is more stable than titanium third and titanium second. Okay. Again, I am telling you that early in the series, scandium is virtually unknown. Scandium second is virtually unknown, and titanium fourth is more stable. Titanium fourth is more stable than titanium third or titanium second. Okay, titanium fourth is more stable. Already I have briefed you. And further I want to tell you, at the other end, the only oxidation states of zinc is +2. That also I told you. No d electrons are involved. No d electrons in Zn. No d electrons are involved. But they have +2 oxidation state. And this, if you see the electronic configuration, then you will come to know D10 is there. No d electrons are involved. The maximum oxidation state of reasonable stability correspond to value to the sum of S and D electrons up to manganese. S and D, just to add, that is the stable oxidation state. The maximum oxidation state of reasonable stability correspond in value to the sum of S and D electrons up to manganese. Titanium oxide TiO2, VO2. In this, if you will see, titanium oxide TiO2, here oxidation state is fourth, and VO2, vanadium dioxide, VO2, here vanadium has 5 oxidation state. Okay. Chromium tetraoxide, CrO4, here chromium is 6 oxidation state. CrO4, 2 minus. Then here chromium is 4th oxidation state, and MnO4, then here MnO4 1 minus, then here manganese is in 7 oxidation state, followed by a rather abrupt decrease. After that, decrease will be there, abrupt decrease in stability of higher oxidation state. So that typical species to follow are ferrous. Ferrous, you know that 2 and 3, oxidation state 2 and 3. That is a ferrous, stable. Already told you. Cobalt, second and third. Cobalt stable is second and third. It is common also. Nickel is only 1, +2 is stable. copper is 1 and 2. 1 and 2 and Zn is only 2. Okay. Actually, sometimes a question is asked related to oxidation state. The variability of oxidation states. Why so many oxidation states are there existing in this transition elements? That reason I am telling you. The variability of oxidation states, a characteristics of transition elements, arises out of incomplete filling of d orbitals in such a way that oxidation states differ from each other by unity. As for example, vanadium 2, vanadium 3, vanadium 4, vanadium 5. Okay. Then this arises out of incomplete filling of d orbitals. Sometimes in d only one oxidation, one electron, other time 2 electron, then 3 electron, then 4 electron, up to 9. Okay. Then this arises variability of oxidation states. This is actually a characteristics of transition elements. Arises out of incomplete filling of d orbitals in such a way that their oxidation states differ from each other by unity. This is in contrast with the variability of oxidation states of non-transition elements. This is in contrast with the variability of oxidation state of non-transition elements, where oxidation states normally differ by unit of 2. Generally, it will differ by unit of 2. An interesting feature in the variability of oxidation states of the d block element is noticed among the group, means group 4 through 10. Groups 4 through 10. Here, interesting feature you will find in the variability of oxidation state of the d block elements. Although in the p block the lower oxidation states are favored by the heavier members due to inert pair effect. In p orbital, in p block, the lower oxidation states are favored. Lower oxidation state are favored by the heavier members. Why? Due to inert pair effect. The opposite is true in the group of d block. For example, in group 6, molybdenum 6 and tungsten 6 are found to be more stable. Remember, in group 6, molybdenum oxidation state 6, tungsten 6 are found to be more stable than chromium 6 and particularly chromium 6. Thus, chromium 6 in the form of dichromate in acidic medium is a strong oxidizing agent, whereas MoO3, molybdenum trioxide, and this tungsten trioxides are not. This you remember that these things here in group 6, molybdenum 6 and tungsten 6 are found to be more stable. Molybdenum and tungsten 6 oxidation state are more stable than chromium 6. Thus, chromium 6 in the form of dichromate in acidic medium is a strong oxidizing agent, whereas MoO3 and WO3 are not. This question is asked. Okay. Again, I want to repeat it because this is the important point, that in the p block the lower oxidation states are favored. They want this lower oxidation state, P block. In the P block, the lower oxidation states are favored by the heavier members due to inert pair effect. The opposite is true in group of D block. For example, means in D group it is not like that. Example, in group 6, molybdenum 6 and tungsten 6 are found to be more stable than chromium and particularly chromium. Thus, chromium in the form of dichromate in acidic medium is a strong oxidizing agent, whereas molybdenum trioxide and tungsten oxides are not. Okay. Now, further I want to tell you, low oxidation states are found when a complex compound has ligands capable of pi acceptor character. Low oxidation states are found when a complex compound has ligands capable of pi acceptor character in addition to sigma bonding. For example, in nickel CO4, nickel tetracarbonyl, NiCO4, nickel tetracarbonyl and ferrous pentacarbonyl, the oxidation state of nickel and iron is 0. Remember it. In this complex, nickel and ferrous, nickel tetracarbonyl and ferrous pentacarbonyl, oxidation state of nickel and iron is 0. Okay, this question is asked. Now, this one question I want to ask or discuss, because this question is asked in examination. Name a transition element which does not exhibit variable oxidation state. Which is the name the transition element? Which transition element is there which does not exhibit variable oxidation state? I have discussed scandium 21. It has only one oxidation state, +3. Okay. Scandium means Z is equal to 21, means atomic number is 21, does not exhibit variable oxidation state. This is the important question. Okay. Now I want to discuss trends in the standard electrode potential. Trends in the standard electrode potential. Then first you should know, already I have discussed many times, again I want to tell you what is the electrode potential. Electrode potential of an atom is tendency to lose the electron or tendency to gain the electron. Tendency to lose the electron, this is the oxidation, process is oxidation. Then how much tendency is there? Less tendency or more tendency? Then this tendency actually is called potential. Okay. Then this actually potential where electron is involved, that's why it is called this. And one more, element. Every element has a tendency to lose the electron or gain the electron. Correct? Then in element is made from the atoms. Finally, atom loses the electron or gain the electron. Then if you consider the electrode, then what is the tendency? Tendency to lose the electron or gain the electron is called electrode potential. When it is a losing tendency to lose that you are considering, then that is called oxidation potential. And when you are discussing for gain of electron, then gain of electron is called reduction, then that potential is called reduction potential. Then oxidation potential, losing of electron, tendency to lose the electron, that is negative value. Okay, it has tendency to lose the electron. Other has tendency to gain the electron. Then you have seen that in this things cell, galvanic cell, when electron was losing, when at a node electron was losing and its potential was negative, and on cathode it was gaining the electron, and the electrode potential was this sign was positive. A node has negative sign and cathode has positive sign, correct? But according to IUPAC, they are considering reduction potential as a standard everywhere. All countries who follow this the what you can say ICUP, this International Union for Applied Chemistry, IUPAC. Those who are following IUPAC all follow reduction as a standard. IUPAC, okay, International Union for Pure and Applied Chemistry. Then according to IUPAC, reduction potential is considered as a standard. Okay, both are equal but opposite in sign. Don't forget. If you are knowing the reduction potential, then just to change the sign. If it is positive, now tell the negative. And potentials are equal, only they differ in sign. Okay. Then here now I am going to discuss trends in the standard electrode potential in term of reduction. In term of reduction, then reduction means, suppose M means metal, M2 plus. After taking the 2 electron, it will convert to M. That's why it is written as a M2 plus oblique M. Means M means it has taken 2 electron and converted into metal, solid. Then it is represented as M2 plus M power 2 plus oblique M. Okay, this is a reduction potential. It is actually, this is represented M2 plus oblique M. This represents reduction. And how much potential is involved here, that is called reduction potential. Then you might have seen one chart is there, electrochemical series. It is in that elements are arranged starting from negative to positive via 0. Correct? Means it starts with negative. As for example, lithium. Lithium has value around minus 3.04. Okay, minus. And slowly this minus will become lesser, then will come 0, and then positive value will start, and finally this auric, that is in positive value, then that which is more negative, more the negative value, more the reaction, more the reactive element is more reactive. Its value, if reduction value is in negative, then more negative value means that element is very reactive, and this whose value is most positive means they are not reactive. Then platinum, After that, this mercury, platinum, auric means gold. Then gold is most positive value. That's why these three elements, silver, platinum, gold, they have positive value. In that auric is maximum positive value. Then that's why they are inert. It will not react with air, water. Okay, it will not react. They are noble metals also, called noble metals, not noble gases, noble metals. Okay, noble gases is last group 18, group 18. Then here I am telling value of negative and positive value. Negative value means more reactive. More the negative, more the reactive. Less the negative, then less reactive. And positive value, as will go to the more and more positive, then will be less and less reactive. Via zero. Zero means that is hydrogen has been considered as zero potential. Simply arbitrary hydrogen H plus will convert to H2, means 2H plus, it will give H2, 2H plus oblique H2. Its value has been simply considered arbitrary as a 0. Above hydrogen they are negative. In negative also, most negative, little less, and it is increasing towards 0. And after that 0 onward, it will be little positive, more positive, most positive. In electrochemical series, you can see the value. Then in electrochemical series, it is arranged according to the most reactive to the least reactive. Okay, via hydrogen gas, 0. Then now this here potential, reduction potential, I told you that here we will discuss that common oxidation state. M2 will convert to M, or M3 plus, it will convert to M. Then in transition elements, what are the trends? How electrode potential is increasing or decreasing? Electrode potential, reduction electrode potential, how their value is increasing or decreasing, that I am going to discuss. Okay, that is called trends in the first I will discuss metal 2 oblique M. Okay, trends in the metal 2 plus oblique M standard electrode potential. Okay, this you can understand by a curve also, or graph. Then in graph you will see that is actually down on x-axis this name of the metals are written, transition metals, group 1. Okay, then they are calculated and observed value, both are written. Observed value and calculated value means theoretical, should be theoretical, but what is actually observed, both value is given here in the curve or graph. Then on x-axis, name of elements are there, transition elements, first group, and y-axis standard electrode potential is given. Then by this graph or curve, here actually you will find, I will try to send this graph. Here I am telling you for explanation purpose, because one is calculated values, other is observed values. Then how will you show these two values? Then these two values is shown in two different color. As for example, that red color, that will tell about the observed value, and green will tell about the calculated value, means theoretical. Okay, That in different, you can say chart different color they can consider, but two different color will be there to separate the two values. Then here interesting point I am telling you that uh, titanium, it starts with, you know that 10 elements are there: titanium, vanadium, chromium, manganese, ferrous, cobalt, nickel, copper, Zn. Okay, 10 elements are there. Then here titanium, you will find that its value is less than 1.5, near about 1.5, you can tell, little less. Okay, 1 minus 1 point, minus 1.5. Actually standard electrode potential is shown on y-axis from -2 to 0.5, means -2 plus -2 volt to plus 0.5 volt. Then here titanium value is near about minus 1.5, less than that. Okay, maybe these things minus 1.7. Okay, not 7, 1.8, you can tell, minus 1.8. Then this is a least value. Titanium has least value of electrode potential. Now vanadium is more. Actually value is decreasing. Its value is actually now more than minus 1.5. More than minus 1.5. It is going towards minus 1. Minus 1.5 means more negative, and minus 1 is less negative, means it is tending towards 0. Then vanadium has electrode potential, you can say roughly, you can tell now this in the term of negative I am talking about that it is a minus 1.5 above value, means now you are increasing towards minus 1, means it is decreasing, value is decreasing, minus value is decreasing. Then vanadium already told you near about 1.7, and vanadium is near about minus 1.3, and after that chromium is now around these things minus 0.6, not minus point, you can tell 3, minus 0.3. Okay, minus 0.3 minus chromium, and manganese is least. In all transition elements, manganese is least reduction potential, least, and its value is now 1.6. Okay, means least. Remember only that list means now list is actually this titanium. List is titanium minus 1.7. But after that, what are the remaining in that? Manganese is least value. Okay. Now after that, these things highest, if you want to know, then I will come to the highest. But after manganese, you just see ferrous. ferrous. Then ferrous is minus 0.5, minus 0.5. But here in all these elements up to ferrous, theoretical and calculated values both are equal. Whatever be the value, but theoretical and calculated both are equal. Now you can see after the ferrous, in cobalt change is there. Cobalt change is there. Means observed values are in positive. Not a fully positive, means now it is a minus you can tell 0.3, minus 0.3, minus 0.3. That is actually for cobalt. This is the observed value, minus 0.3. But now these things calculated value is different. Calculated value is different. Now its value is now can say in minus. I am talking about there is a difference of around 0.3 volt. 0.3 volt in minus difference is there among both. Okay, means now you can consider as a 0.7 in minus 0.7, and other is around 0.8 or 0.9 roughly. Then maximum 0.3 you can tell difference is there in volt in case of cobalt. And nickel also difference is there, 0.2 volt difference is there. Both values are in negative, means one is now you can tell 0.4, 1 is 0.4, and other is now around 0.2. Then here also 0.1 difference is you can tell, 0.2 difference you can tell, 0.2 difference volt, minus. Both all are in minus. Now after that very important thing I am telling you about the copper. Copper is in plus. Copper is in plus. Its value is 0.3, plus 0.3 volt. 0.34 already you know. Exact value is 0.34 volt. 0.34 volt exact value for cobalt. Then here theoretical and calculated both values are same, but it is in positive, and before copper all are in negative. This you remember. And again Zn, you will come to the Zn. Then Zn you know that its value is this minus 0.76 volt exact. Minus 0.76 volt. Okay, for Zn. But theoretical and calculated almost same, very less difference are there, almost same you can tell. Okay, 0.1 difference is there. Then this I have told about the these things, trends in the standard electrode potential in group 1. In group 1, this series 1 transition elements. Little more I will discuss. Okay, that thermochemical parameters related to the transformation of solid metal atoms to metal 2 plus ions in solution. Just to remember, thermochemical parameters related to the transformation of the solid metal atoms to M2 plus, means oxidation actually, from the solid metal means M you are talking about, M2 plus ions in solution. Okay, their values we are telling you. Okay, the observed values of standard electrode potential E0 are those calculated using the some values, standard values are there. According to using that value, this for each element standard value is calculated. Now come to the point, the unique behavior of copper. The unique behavior of copper having a positive E0 value accounts for its inability to liberate hydrogen from acids. This is very, very important. This is the unique behavior of copper having a positive E0 value. Positive means it will not lose the electron further. Okay, it has no tendency to lose the electron. This is the unique behavior of copper having a positive standard electrode potential. What is the reason for unique behavior? This accounts for its inability to liberate hydrogen from acids. Then in acids it will in the form of H plus. Then H plus require electron. Then hydrogen is not in a position to lose the electron. Okay. Then hydrogen is considered as a standard, you know. Then this is the unique behavior of copper. This accounts for its inability to liberate hydrogen from acids. Only oxidizing acids means nitric acid and hot concentrated sulfuric acid react with copper. Always remember. Only oxidizing acids, as for example nitric acid and hot concentrated sulfuric acid, react with copper. The acid being reduced. Acid will be reduced. Okay. That also in the two acid I told, nitric acid and second is hot concentrated sulfuric acid react with copper. The acid being reduced. Acid will be reduced. The high energy to transform copper to Cu2 plus from copper metal means solid to Cu2 plus is not balanced by its hydration enthalpy. Okay. The high energy of transformation, the high energy to transform copper solid to copper 2 plus is not balanced by its hydration enthalpy. The general trend towards less negative E value means standard electrode potential value across the series is related to the general increase in sum of the first and second ionization enthalpies. This you should understand, the general trend towards less negative standard electrode potential, that value across the series. Why it is less negative, that I am telling you. The general trend towards less negative E0 means electrode potential values across the series is related to the general increase in the sum of the first and second ionization enthalpies. It is interesting to note that the value of standard electrode potential for manganese, nickel and Zn are more negative than expected from trend. This you remember. Okay. That value of standard electrode potential for manganese, nickel and zinc are more negative than expected from trend. Already I have discussed. One question is asked that I want to discuss. Why is chromium, why is Cr2 plus reducing and Mn3 plus oxidizing when both have D4 configuration? This question is asked. Why is chromium Cr2 plus reducing and Mn3 plus oxidizing? One is reducing, other is oxidizing when both have D4 configuration. Why? This question is asked. Then already I have given hint, but now I am explaining it. Chromium is reducing and Mn3 plus is oxidizing. Why? When both have D4 configuration. Then now explanation I am telling you. Cr2 plus is reducing as its configuration changes from D4 to D3. D4 to D3 means it is losing one electron. D4 to D3, it lost one electron. Correct? The latter having a half filled T2G level. That is this thing, manganese. Manganese, you have to see, that is having a half filled T2G level. Again I am telling, chromium is reducing as its configuration changes from D4 to D3. Then what happens for the reducing agent? They will give electron to the others. Other will take the electron. Correct? Other will take the electron. Then reducing agent will lose the electron. Then that's why D4 to D3. That one electron, now it was having 4 electron, now it is 3 electron. That one electron given to the others, which has to the others, okay, in the reduction process. Then after that I am telling you, on the other hand, the change from Mn2 plus to Mn3 results in the half-filled D5 configuration, which is extra stability. In case of manganese, I told you manganese is half-filled. Then Mn is in plus 2. Now when it will lose one electron, Mn2 to Mn3 plus, it has lost one electron, then this results in the half-filled D4. Now it was in D4, now it became D5. It has taken one electron. D4 became D5. Okay. Then this happened from the s orbital, one electron was there. Then D4 was there, then it had taken one electron. Then in s orbital it became only one, and from S2 that it become S1 only, and D4 became D5. Then this Mn2 plus to Mn3 plus, by doing all the things, result in the half-filled D configuration, which is extra stability. That's why chromium reduces. Chromium is a reducing agent, and Mn3 plus is oxidizing agent. Then for the oxidation, oxidizing agent, reducing agent. For the oxidation agent which are responsible for oxidation, means it will take the electron. And other will lose the electron. A will lose the electron, and B will take the electron. Okay, then A is losing electron due to B is taking that electron. Then this process is oxidation, and for this process B is responsible. Then B is called oxidizing agent. Reverse case, reducing agent, that A is losing electron and B is taking electron. Correct? Then process is reduction. A is giving electron to B is taking. Process is reduction, and for this reduction A is responsible. That's why A is called reducing agent. This is the explanation. Now further I will discuss trends. But here just some data I want to tell you for thermochemical data, kilojoule per mole for the first row transition elements, and the standard electrode potential for the reduction of metal 2 to metal means M2 plus 2 M. How much this potential is required? Change in potential from M2 plus 2 M. For all 10 elements, I will tell you delta H value I will tell, and I will tell this electrode potential in volt. Then here titanium, actually here also I want to tell you that this delta H value, then here first ionization, second ionization value I will tell you. Okay, and hydration value also I will tell. 3 value I will tell. First ionization energy, second ionization energy, and this hydration energy I will tell you, and finally I will tell standard electrode potential when M2 plus converts to M, means a solid metal. Then first titanium I want to tell you. Then titanium, actually this first ionization energy is 661, and second ionization energy is 131310, and then you add both, then what will roughly 661 plus 1310, it will become 1971 kilojoule per mole. Okay, and this hydration energy is minus 1866, and this was 1971, means hydration energy is in minus, and this 1900 is a positive value. Okay, then in this case means positive value, both if you will add first and second ionization energy, then it is more than hydration energy, which is minus 1866, and this was 1971. Then in that case its electrode potential, standard electrode potential in the process M2 plus 2M is minus 1.63. Now vanadium, then vanadium is first ionization energy is 648, and second ionization energy is there, that is the 1370, and hydration energy is minus 1895. Correct? Then again if you will add first and second ionization energy, it is more than hydration energy, and its standard electrode potential is little increasing, minus 1.18, minus 1.18. In first case it was minus 1.63. Now chromium. Chromium first ionization energy is 653, second is 1590. First and second meaning you are understanding. To remove first electron, that is easily you can remove, that's why its value is less. Second, removal of the second electron, which is little closer to nucleus. To nucleus has more attraction for these things. Second, and outer has less effect on the outermost electron. That's why their value is less, and second one value is more, and third one again further more. Okay. Then now chromium, third one, I told you its value is 653 plus 1590 for the second, and for this delta H value is minus 1925. Minus 1925 means became more. First case it was the minus 1866, and second case minus 1895. No, more minus. Now in this case minus 1925, further more delta H value. Okay. Then now again you will see the difference. Then now we will find that in case of chromium also, and there's a delta H1 plus delta H2 value is more than hydration energy. Okay, and its standard electrode potential for vanadium, for chromium, that is minus 0.90. Like that way, manganese 716 plus 1510, and that is again 2200 something, it is coming 36, and hydration energy is minus 1862. Now it is becoming now more, minus 1862 began to increase. Then here E value, standard electrode potential, is now minus in minus only, till that it is minus 1.18. Okay, minus 1.18 means reaction will take place in all these four cases. Reaction will take place fast. Okay. Now ferrous is 762 plus 1560, and delta H value is minus 1998. Okay, minus 1998, more negative, and its value is minus 0.44. This is also in minus. Like that way, cobalt 757 plus 1640. You see, always first ionization energy value is less than second ionization energy, and hydration energy all are in minus only. Then in case of cobalt, in case of manganese, I told you ferrous 762 plus 1560, and standard electrode potential is minus 0.44 volt, and cobalt is again 757 plus 1640, and hydration energy is minus 2079, more negative, and its value is standard electrode potential is minus 0.28. Okay, then reactivity, more the negative value, more the reactive, more reactive. Okay, then now this is decreasing actually. If you will see the value electrode potential, then now it is this minus value from the minus 1.63 become minus 1.18, again further means minus 0.90 increased actually slowly and slowly, and after that again decreased 1.18, now again decreased minus increased 0.44 minus 0.44, that is for iron, again increased in case of cobalt minus 0.28, again further increase in the case of nickel 736 plus 1750, and this hydrogen energy is minus 2121, and again it is minus 0.25. All are minus except copper is 0.34 plus value, only one. Then its copper first oxidation energy is 745 and second is 1960, and hydrogen energy is minus 2121, and E value is 0.34, and last is Zn, that is the one, this is 908, and this value second is 730, and hydrogen energy is minus 2059. Okay, then now its value is minus 76, minus 0.76. This is also important value for solving during the solving the numericals. Copper and Zn value is generally used. Okay, then actually this hydrogen energy is compensating. Actually minus value, delta H is minus value, means heat is going out, it is releasing heat, and positive value means it requires heat. Then what is the difference between two? That is actually responsible for this things, electrode potential. That difference is responsible for electrode potential. Okay, this you remember. The stability of the half-filled D subcell in Mn2 plus and the completely filled D10 configuration in Zn2 plus are related to their standard electrode values, whereas standard electrode potential for nickel is related to the highest negative delta H hydrogen value. Nickel, this value is highest, minus 2121. Okay, for nickel minus 2121 is the hydrogen energy. Then for standard electrode potential for nickel is related to the highest negative delta H hydrogen. Okay, now I want to tell about the trends in M3 plus to M2 plus. M3 plus to M, this is also reduction. M3 plus, now it is becoming M2 plus, 1 electron difference. Okay, they have M3 have taken 1 electron, that's why it became M2 plus. In that case, what are the trends? I am telling you. Trends in the M3 plus oblique M2 plus standard electrode potential. An examination of, if you will observe the values, okay, then we will find the low value for scandium. The low value for scandium means low value for electrode potential. The low value of scandium reflects the stability of Sc3 plus. Low value low electrode potential for scandium. Due to that, scandium 3 plus is stable. Why scandium 3 plus is stable? Then it is due to the low value of standard electrode value for scandium. Yeah, it has low value. Now this I told you that scandium reflects the low value for scandium reflect the stability of scandium 3 plus, which has a noble gas configuration. Scandium 3 plus has a noble gas configuration. The highest value for Zn, the highest value for Zn, that is a minus 0.76. Okay, the highest value for Zn is due to the removal of an electron from the stable D10. Question is asked. D10 is stable, then from that if electron is removed, then it is difficult to remove. It will require more energy. The highest value of Zn is due to the removal of an electron from the stable D10 configuration. If energy required is more, then electrode potential will be reduction potential will be more. Then the highest value for Zn is due to the removal of an electron from the stable D configuration of Zn2 plus, because if you remove Zn2 plus means you are getting D10. The comparatively high value for manganese, again important this question I am telling you. The comparative high value for Mn, so that the Mn2 plus means D5 is particularly stable. Okay, this question is asked. Why this is a high value for electrode potential. The comparatively high value for Mn, so that Mn2 plus, that is in D5, is particularly stable, whereas comparatively low value for iron shows the extra stability of F3 plus means D5. It is also in D5. And F3 plus, if we remove 3 electron, then it will be D5 configuration. Last d orbital will have 5 electrons. This is the extra stability. Then that's why Fe3 plus is stable. Fe2 plus is not stable. Fe3 plus is stable. Okay, then this I told you, comparatively low value for Fe shows the extra stability of Fe3 plus means D5 configuration. The comparative low value for vanadium is related to the stability of V2 plus means half filled T2G level. Okay, then today I am stopping only here. Next class again I will continue with another terms, means trends in stability of higher oxidation states. Thank you.